So in this next problem, we've got a African swallow, you don't get it into Monty Python reference, carrying a coconut. The African swallow is traveling at a speed of 18 meters per second, and at a, well, let me write that down below, 18 meters per second, and as a height of 100 meters. The swallow then drops the coconut. It falls some distance away, which we'll call x, in some time t. So, first thing is that it's a two-dimensional kinematics problem. I start off my kinematic problems by always creating a table, and this problem is perfect for that. Okay? Here is my table. Okay? So I'm talking about my x direction, which is this direction, and my y direction, which is this direction. Okay? My x and my y. Now I'm looking for acceleration, velocity initial, velocity final, I'm crossing out my lines, position initial, position final, which we can simplify by just saying displacement, and time. Now time is the only thing that travels across both of them equally because it's not a scalar. The other ones are scalars, and scalars means that anything that happens in the x direction is independent of whatever happens in the y direction, with the exception of time. Okay? First of all, acceleration. Acceleration in the x direction, this way. There's nothing pulling the coconut this way or pushing it that way. Most of these problems we ignore air resistance, which would be our primary motivation of pushing the coconut backwards. So, because there is no air resistance, we'll say that the acceleration is 0 meters per second. Now, in the y direction, it's being pulled by the force of gravity. That means that it has an acceleration of 10 meters per second, and it's negative. It's pointing downwards. Okay? The initial velocity in the x direction, or how fast it's moving this way, is 18 meters per second, and because there's no acceleration in the x direction, the final velocity is going to be the same value. Why is that so? Well, remember, acceleration by definition is a change in velocity. Because that value is 0 means that there's no change. Now, in the y direction, in this direction, it starts off as 0. It's not being thrown down, so it doesn't have any motion in this direction initially, but is quickly taken by gravity and accelerated downwards. By the time it hits the ground, it does have a velocity, obviously, but we don't know what that is. Okay? Next, we have initial position in the x direction. I'm going to set that equal to 0. It's my call. It doesn't make a difference. The final position is an unknown. Okay, in my y-axis, I have an initial height of 100 meters, and I have a final height of 0 meters. Now, there are things that I can do to change that around. I can say that this is 0, this is a negative 100, but it all works out the same. And then finally, time. I don't know. Okay? Now, how we solve these problems, how to solve kinematic problems, it's actually kind of simple. There's a couple of really easy ways of doing it. And I'm clearing this off so I can make room for equations. We usually start off by doing one of two things. Determining the height here by using time, or determining the time by using height. Okay? In this case, we don't know the time, so we're going to use the height, which is a known, to determine the amount of time it takes for it to hit the ground. Okay? How we're going to do that is this. X final, well, sorry, not X. Y final minus Y initial, or Y final equals Y initial plus V initial in the Y t plus 1/2 the acceleration in the Y times time squared. Now, putting in my zeros really quick, my position final is 0, my initial position is 100, my initial velocity is 0, time still remains unknown, plus 1/2 negative 10, or not negative 100, negative 10, 1/2 times negative 10 times time squared. Goes away, goes away. Bring this over to the other side. I'm left with negative 100 meters is equal to negative 5 meters per second per second. Keep forgetting to put my units there. T squared. So bring that over. I'm left with 100 over 5 is equal, don't forget my units, meters per second, which translates, I'll just do the math really quick, 20 seconds squared equals t squared. Take the square root, and I'm left with the square root of 20, s equals t. Now, s stands for seconds, obviously. So that means my time is going to be square root of 20. Okay? That's the amount of time it takes for the coconut to drop and hit the ground. Now, it's also the amount of time that the coconut has before it hits the ground to travel a distance in the x. It's the same time. Okay? So, for the first part of the problem, it was pretty simple. All we did was solve for the time by using my y information. What I'm going to do now is use the only thing that translates from y to x, and that's time, to solve for the final position. Okay? I'm going to do that using x final is equal to x initial plus v initial t plus 1/2 a t squared. X final, I don't know. X initial is 0 meters plus my initial velocity, 18 meters per second. Okay? This time I do have time, square root of 20 seconds, plus this term with the acceleration equals 0 goes to 0. Okay? So that means that my unknown, my x final, is equal to 18 times the square root of 20, 18 meters per second times the square root of 20 seconds. Okay? Square root of 20 is going to be the square root of what approximately gives me 20 that's squared. Between 4 and 5, say 4.5, more like 4.3. So that's 18 meters per second times about 4.3 seconds. The seconds cancel off. I'm left with meters. I get 18 times 4.3. 3 goes 24. 2, 5. Gosh. Why am I doing this? Use a calculator. 4, 2, 5. And then, crap. 32. And 4, 7. So we're looking at a value that's approximately equal to 4.77 meters. So that means that it lands a distance of about 78 meters away from where it drops. Okay? A pretty simple problem, but one that you have to know because this is the prototype AP Kinematics problem. You will see this problem on the AP exam. Almost every single exam I've ever seen has a problem that looks almost identical to this. Maybe not an African sparrow, maybe more a car running off a tabletop or a ball rolling off a tabletop or something along those lines. But this is the prototype kinematics problem for the AP exam.